Hi all. Until I decide on how I want to deliver these lessons on classical mechanics, I will discuss two more examples on how one goes about solving problems related to the calculus of variations. So let's start with the first example. So we want to find the line which, if it's revolved around an axis, it produces a surface of minimal area. So consider the surface generated by revolving a line connecting 2 points, 2 points, I'm sorry. Let's call them x1, y1 and x2, y2 around the y-axis. So the line connecting these 2 points is revolved around the y-axis, okay? And I'm gonna show you a scheme. So around the y-axis, find the equation of the line such that the generated area, so that the generated surface, surface has a minimum area. Right, so let me use a clean, start a clean page. So this is your x-axis and this is your y-axis, and then you have one more axis that doesn't play a role in this problem. So let's use red. So I have a point x1, y1, and maybe another point x2, y2, okay? And these points are connected by a line, so many lines can pass through these points. I mean, an infinite number of lines, in fact, can pass through these 2 points. So we want to find that line that if revolved around the y-axis, and this is the y-axis, right? So if it's revolved around this axis, meaning that you will get something like this. Okay, hope this makes sense. And then down here, the surface will look like this. So you see how we get the surface, okay? And this is the, oops, let me use a different color. And this is the surface area, right? This is not visible. Let me use a different color. So this line is connected. And then let's use orange, maybe. Okay. So this is the generated surface, all right? So we want to find the equation for this line over there. So that's going to be a function of x. So it's going to be a function of, sorry, a line with equation something like y equals y of x. Okay, so we want to find the equation of this line such that the generated surface area is a minimum. So we need to optimize, in this case minimize, a surface. Okay, so in a previous video I said that in these problems related to the calculus of variations and the Euler equation, you need to start by expressing the quantity you need to find in the form of an infinitesimal quantity to begin with, and then turn that into an integral, okay? So, and then that integrand, so the integrand under the integral should be expressed then as a function of y, and then its first derivative, y prime, and x. Not all of these variables appear in the integrand at all times, and that integrand is called a functional. So we need to write down an integral involving a surface and express the integrand in terms of y, y prime, and x. Okay, so how are we going to do that? Okay, so first of all, notice that, and I have already drawn something like a strip of this on this surface. So if we cut this part, okay, this is a part with let's assume that this little piece over here, okay, that's some infinitesimally small piece of this line connecting points x1, y1, and x2, y2. Okay, so that's a piece of that line, right? And then if we unroll this strip, you can think about the infinitesimal area. So what I'm trying to say is that if the infinitesimally small piece of that strip has an area of dA, then that dA is going to have a surface area equal to 2 pi x, y 2 pi x, because this radius over there is x, right? So if I unroll that strip, I'm going to get something that is going to look like a square pretty much, okay? Sorry, not a rectangle, I'm sorry. And the width of that strip is going to be 2 pi x, because we revolve this, because this is a circle pretty much of radius x, right? And this x varies. So the x up there and the x down there are different. Therefore, we somehow have to integrate that x, okay? I hope this makes sense. And now this piece over there, ds, right, is going to be the height of this rectangle. And what will that ds be equal to? It's simply going to be equal to dx squared plus dy squared, okay? So that ds, if this is ds, it pretty much has, we think about it as an infinitesimally small triangle with sides dy and dx, okay, ds itself being the hypotenuse. Okay, then some of you will protest that this is not, if you unroll that strip, that's not really a rectangle, that's a trapezium, which is sort of true, but we are talking about infinitesimal quantities, so this is the appropriate infinitesimally small area, okay? So if we mix those two together, if we plug ds, I'm sorry, and this should be ds, not ds squared, okay? So if we plug ds into the dA, we get 2 pi x and then the square root of dx squared plus dy squared, okay? Something like that is a typical thing that appears in this calculus of variations business, if you can call it business. So this is 2 pi x, and then we can take the dx out of the square root. I'm going to do that in a moment. So we get this expression, and then we get 2 pi x dx, and then the square root of 1 plus the first derivative of y with respect to x squared So the area is pretty much the integral of, we can take the constant out, 2 pi, and then x square root of 1 plus y prime squared, and then dx. And this should be integrated from x1 to x2, right? So what have we achieved here? We pretty much found the functional we need, right? So this is the functional f, which is, so I think I never mentioned this in the previous video, but a functional is a function of a function, okay? Because y and y prime are themselves functions of x. So this is why we write this functional using that semicolon over there to specify that the independent variable is x, and then you have y prime and y being the dependent variables, and with the independent variable being x, but then the functional itself treats everything like a variable, okay? So as far as the functional goes, y prime, and x are just variables, okay? I hope this makes sense. If it doesn't, ask me in the comments and I will provide answers if I know the answer, okay? Now, this functional, let's write it down. So our functional f is x square root of 1 plus y prime squared. Okay, let's call this equation 1. Okay, to find the minimum path, that is the line y equals y of x that minimizes the surface, this functional has to satisfy the Euler equation, okay? So the partial with respect to y, I'm writing down the Euler equation, minus d over dx of the partial with respect to y prime should be 0, okay? So if we plug the functional into the Euler equation and solve, we will find the y that minimizes the surface in this case, okay? So we can plug equation 1 in, okay? And the first observation is that the partial with respect to y is 0, right? Because we have no y dependence in the functional, so that's nice. So we can immediately integrate. So the partial with respect to y prime should be a constant, right? Because we need the first derivative with respect to x of this partial with respect to y prime to be 0. And the only way for that to happen is for the first derivative, of the partial of the functional with respect to y prime to be a constant, okay? And again, when we take the first derivative of this quantity over there, partial with respect to y prime, we don't take the derivative with respect to x, okay? Because y prime, and x are treated as independent variables, okay? Now let's go take the partial with respect to y prime. So x is a constant as far as the partial with respect to y prime is considered. And then we have 1 over 2 times the square root of 1 plus y prime squared, and then times 2 y prime. This whole thing should be a constant. Let's call it c. All right. So we pretty much have to solve this differential equation now to find the equation of the line we are interested in. So 1 plus y prime squared, and then in this equal to c. Let's take the square of both sides. X squared y prime squared over 1 plus y prime squared should be equal to c squared. So the square root in the denominator goes away. So x squared y prime squared is equal to c squared plus c squared y prime squared. So we have y prime squared, and then x squared minus c squared equal to c squared. So we keep going. I'm gonna skip one step. and write that y prime should be equal to c over the square root of x squared minus c squared, okay? And then we can integrate this. Wait, we cannot integrate it yet. We have to write dy and then integrate that is equal to c dx over the square root of x squared minus c squared, and then integrate that. And you can use a table of integrals or anything you like to find that y should be equal to c and then times cosh of to the minus 1, the inverse cosh of x over c, the constant, plus b, which is another constant, okay? And there is another way to write this function. We can write x with respect to y, and if we do that, we find x is c and then cosh of y minus b over c, and this is the equation of a catenary, okay? And this is the equation of the line. Now, if you want to find the constants b and c, I'm going to write this as a note to find b and c, demand that the line passes through the points x1, y1, and x2, y2. Okay, simple as that. But I'm not going to show the form of this plot, but this equation, or equivalently this equation, give you the function y that minimizes the generated surface, okay? Which I think is kind of cool, like starting all the way here, you just apply, you find the functional, and then you apply the Euler equation to find what you need. Now, I'm gonna solve another example, and this example should have been the first example in the calculus of variations because it's the simplest, but I don't know, I just did it this way. So let's see another example before I stop the video. So we have to show that the shortest distance between 2 points that happen to be on a plane, so 2 points on a plane, is a straight line. Okay, so this is my y, this is my x, this is my plane, and I have 2 points. Let's use red again, like before. So here is my x1, y1, here is my x2, y2, and then this is a line connecting them. There is an infinite number of lines that pass through these 2 points, but we have to find the shortest, the one that allows you to move from x1, y1 to x2, y2 in the minimum possible distance, okay? So the line that has the minimum possible length, pretty much, okay? So since you are dealing with length, you suspect it, you take an infinitesimally small piece of this line, and this piece is gonna have a length ds, and if we zoom in, this ds is the hypotenuse of a right triangle with sides dx and dy, okay? This is standard when you are dealing with the calculus of variations, okay? So let's write it down. Let's write down this infinitesimally small piece length. So ds squared is dx squared plus dy squared. So ds is the square root of dx squared plus dy squared. And this length is what we need to find. So ds is, we take this dx outside the square root, so 1 plus y prime squared, okay? So s, the length of this line, is the integral from x1 to x2 of the square root of 1 plus y prime squared dx. This is our functional f, okay? And we plug this functional into the Euler equation. So partial with respect to y minus d over dx of the partial with respect to y prime should be 0. We also get this nice cancellation again because the functional does not depend on y, okay? So the partial with respect to y prime should be a constant, and the partial with respect to y prime is simply 1 over 2 times the square root of 1 plus y prime squared times 2y prime, and this should be a constant. So y prime over the square root of 1 plus y prime squared is a constant, so we take the square of both sides, y prime squared over the 1 plus y prime squared is c squared. So y prime squared is equal to c squared plus c squared y prime squared. So y prime squared 1 minus c squared is equal to c squared. So we have that y prime squared is equal to this quantity here, c squared over 1 minus c squared, and we can cast this into a new constant, call it let's call it k squared, okay, because c squared over 1 minus c squared is a constant, okay. And then we just find y prime is equal to plus or minus k, and this is the simplest, one of the simplest differential equations on earth, because we get this, and then by integrating we find the equation of the line as y is equal to plus or minus kx plus some other constant, let's call it m, okay. And what is this now? This is the equation of a straight line, right? Simple as that, but proven with calculus of variation machinery. And as before, if you want to find k and m, you demand that this line passes through your points x1, y1, and x2, y2. Okay, and this is it for this video. I hope these videos are helpful. I will try to upload more videos, and let me know what you think about them in the comments. Please like and subscribe and so on.